Hi everybody, we're here with our next video titled The Greatest Integer Function. I'm bringing the greatest integer function up here in the limit chapter because it is a really fun function to use with limits. So it's pretty simple, but it's new. So let's take a look at the definition. The floor function, also known as the greatest integer function, so two different titles, is defined as, now check this notation out, it's f of x equals the greatest integer function of x. It kind of looks like an L and then a backwards L kind of around the x. And the definition of this is that this function is equal to the largest integer less than or equal to x. Seems simple enough. But I don't know what this looks like. Like, I know a couple things from my math past. Like, I know that if I'm graphing f of x equals x, it's a linear function with a slope of 1. It's my linear family. And I know if f of x equals x squared, well, that's my quadratic family. And I know if f of x equals x cubed, let me change colors here so we're not getting confused, that's my cubic family. And I know that if f of x is equal to the sine of x, I'm now in my trig family, and sine of x looks like this, right? So every function family follows some graphical rules, some particular shapes. I could do my exponential family, my logarithmic family, but this is my greatest integer family, and I don't know what it looks like. When I don't know what a function looks like, I often will just make a table. And then I'll plot points, and that gives me an idea of the shape. So keeping in mind that my f of x here is my greatest integer function of x, I'm going to fill out this table. So what I did here on my table is I chose some negative integers, 0, and some positive integers. Notice I left some space in between, and we'll get to why in a second. But let's actually just focus on the bottom half of the table right now. Let's start with 0. So if I would plug 0 into f of x, this is what I would have. I would have that f of 0 equals the greatest integer function of 0. And then I have to look at my words here. So I'm looking for the largest integer less than or equal to x. So I need the largest integer less than or equal to 0. 1 second, I'm getting something here. Okay, sorry, I had a little glitch there. I don't know if the video glitched or what, but okay. So I need the largest integer largest integer less than or equal to 0. So that would be 0 because 0 is less than or equal to 0. So I'm going to put 0 here. And then I'm going to come over to my graph and I'll plot a point at 0, 0. Simple enough. Okay, let's go down to 1. f of 1. So if I do f of 1, that's the largest integer less than or equal to 1. Well, the largest integer that's less than or equal to 1 is 1. So I have a point at 1, 1. Okay, let's go down to 2. f of 2 is the largest integer less than or equal to 2. Well, that would have to be 2. So 2, 2. Well, what the heck? This is looking linear to me. If I connect the dots, that's looking like y equals x to me, kind of like my linear family. And this is why I left all this space here, because what's interesting is what happens between the integers. So like, for example, let's go to between 0 and 1. Let me choose 0.1. 0.1. Okay, if I do f of 0.1, then I have to say to myself, okay, what's the largest integer less than or equal to 0.1? Well, 0.1 is not an integer, so I have to go to the largest integer that's less than this. So that kicks me back to 0. So if I go to 0.1, I'm still at 0. I'm going to put that dot right up next to the first dot. Okay, and if I do 0.2, f of 0.2 is the largest integer less than 0.2? Well, that's also 0. In fact, all decimals, all real numbers here between 0 and 1 will kick back to 0 because the greatest or the largest integer less than these decimals is going to be 0 because you have to go less than, not greater than. So even up to 0.9, I have to go less than. So 0.9 is still going to be 0. But when I get to 1, I jump to 1. So this is the way this graph is going to look. It's going to be flat. It's going to be horizontal between 0 and 1. And then right when I get to 1, I have to jump up to 1. So in order to see what's happening here, I'm going to put an open dot to show that f of 1 jumps up to 1. And then between 1 and 2, well, if I do 1.1, the largest integer less than that is 1. If I do 1.2, it kicks me back to 1. Even at 1.9, it's going to kick me back to 1 until I jump to 2. So this one's going to look like this. Go, 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 jump up to 2. Then this is going to go, 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 jump up to 3. And go, 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 jump up. So you can see it almost looks like a staircase coming up. And if you follow this same pattern, you can fill in the rest of this table. So what will happen is, let's see, at -1, well, the largest integer less than or equal to -1 is itself -1. Same with -2. So I can plot -1, -1, and I can plot -2, -2. And as I'm going through here, if I go between 0 and 1, like if I say -0.1, well, the largest integer less than this keeps me at -1. I have to bump back to -1. And -0.2 is -1. Even -0.9 is -1. So this is going to stay here, 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 here at -1 and jump. And this guy here and jump. And et cetera, et cetera, et cetera. So this is the graph of your greatest integer function. Okay? You can see why this is fun to do limits with. If I just do a couple of limits here, let's see, number 1, let's do the limit as x approaches 2 of the greatest integer function of x. The limit as x approaches 2. Now, if you're looking at the graph, we can just go to x equals 2. And we can see that the limit from the left does not equal the limit from the right. We can see that this is coming toward 1 and this is coming toward 2, so this would be DNE. But we could separate them. I mean, we could do them in isolation. We could do the limit as x approaches 2 from the left of the greatest integer function. And 2 from the left would just simply be 1. And, you know, and you could do it even if you didn't have this graph, you could easily do it because if you were plugging in something just to the left of 2, like 1.9, you put 1.9 in there, what's the largest integer less than or equal to 1.9? Well, that's 1. But up here, if you didn't have the graph, you would have to go left and right. So if you put 1.9 in, you get 1, but if you put 2.1 in, you get 2, so they're not equal, so that's a DNE, okay? You can't just plug the integer in and say, oh, it's 2. No, you got to go left and right. Say number 3, say you do something like the limit as x approaches, I don't know, 1.5 of the greatest integer function of x. Well, let's go to 1.5, so that's right here, 1.5. And if you look both from the right and the left, we're at 1. And you can check that. I mean, if you put 1.4 in, it's going to kick you down to 1. If you put 1.6 in, it's going to kick you down to 1. So you're safe to say that that's 1. So you can just have some fun with limits. Just want you to know what the floor function or the greatest integer function looks like and why. It's just a new function to add to our families of functions. Okay, thanks.